So for 10.1, we're comparing two proportions. The conditions for that are simple random sample, normality, and independence. For simple random sample, it'll say that in the problem. For normality, it's about if successes and failures are greater than 5 for significant tests and greater than 10 for confidence intervals. And independence, like most problems with conditions, is that it has to be less than 1/10 of the population. So we're testing populations. You can do a confidence interval, and there's the equation for that. Significance testing, you use P sub C, and then you also use Z for a two-sample Z test. H naught is usually P1 equals P2, and HA is usually P1 does not equal P2, P1 is less than P2, or P1 is greater than P2. So here's a 10.1 example problem. At his high school, freshman Jerry wants to know if seniors are more likely to going to the prom than juniors. He conducts a survey and finds out that 47 out of the 68 seniors in his SRS are going to prom, and that 53 out of the 75 juniors in his SRS are going to prom. Construct a 95% confidence interval for the difference in proportion of seniors going to prom and juniors. So we're interested in the difference in proportion of seniors going to prom compared to juniors. We will conduct a 95% confidence interval. If you check all the conditions, it's random, normal, and independent, and you can see all the work there. And the probabilities are there too. PJs, P juniors, and PSs, P seniors. So there's the formula for the confidence interval. And the interval comes out to be 0.136 to 0.160. And to conclude, we are 95% confident that the true difference in proportion seniors going to prom compared to juniors is captured by the interval 0.136 to 0.160. In 10.2, we looked at comparing two means. When both population standard deviations are known, a two-sample Z statistic is the basis for inference about mu1 minus mu2. The result of this is the standard error, which is the estimated standard deviation. The same conditions are used as in proportions like we did in 10.1. When population standard deviations are known, we use Z, and below is the equation we use to find that. When they are unknown, we use T, and below is the equation to find T. For confidence intervals, when we don't know the means or the standard deviations, we use the equation below with T. For hypothesis testing, without knowing means and standard deviations, we find T with the equation below. Here is a 10.2 example problem. In a packing plant, a machine packs cartons with jars. It is supposed that a new machine will pack faster on the average than the machine currently used. To test the hypothesis, the times it takes each machine to pack 10 cartons are recorded through random sampling. The results in seconds are shown in the following table. So we have the new machine, and we have the mean and standard deviation, and the old machine, we have the mean and standard deviation. So to solve it, we have to check the conditions. Is it independent? Yes. It is less than 1/10 of the population. Random? Yes. And the problem states the randomness. Normal, because n is less than 30 for both samples, we must look at a normality plot. When you do on your calculator, it is shown that they're both normal. So to continue to solve this problem, we'll conduct a two-sample t-test. Our H naught is going to be mu1 minus mu2 equals 0, and our alternative hypothesis is going to be mu1 minus mu2 is less than 0. We're going to make our significance level 0.05. And so when you go on the calculator, you're going to need to do menu 672. And when calculated, t equals negative 3.4, your degree of freedom is 18, and your p-value is 0.00162. We're going to reject each not because our p-value is less than 0.05, and then we conclude that the new machine packs faster than the old machine on average.
Problem number 5 on the 2014 AP deals with the topics in Chapter 10. The problem is, a researcher conducted a study to investigate whether local car dealers tend to charge women more than men for the same car model. Using information from the country's tax collectors' records, the researcher randomly selected one man and one woman among everyone who had purchased the same model of identically equipped car from the same dealer. The process was repeated for a total of 10 randomly selected car models. The purchase prices and the differences, woman minus man, are shown in the table below. Summary statistics are also shown. Do the data provide convincing evidence that on average women pay more than men in the country for the same car model? To solve the problem, we use the 4-step method. We are interested in the true mean difference, women versus men, for the population. We will test the hypothesis at an alpha equals 0.05 level. The null hypothesis is mu equals 0, and the alternative hypothesis is mu is greater than 0. We will use the paired t-test once we check the conditions. We know that it is random because it is stated in the question that the cars were randomly selected. We know that it is normal because even though the sample size is small, the dot plot shows a normal distribution. We know that it is independent because 8, the sample size, is less than 1/10 of the total cars. We can assume that the price of one car does not affect the price of another. To solve the problem, we use that 7 is the degrees of freedom. The t statistic is 3.1178. We find a p-value of 0.0084. Since the p-value is less than alpha, which equals 0.05, we reject the null hypothesis. We have evidence to conclude that on average women pay more than men for the same car. Problem number 3 in the 2009 Form B AP test also focused on the topic in Chapter 10. A French study was conducted in the 1990s to compare the effectiveness of an instrument called a cardio pump with the effectiveness of using the traditional CPR in saving lives of heart attack victims. Heart attack patients in participating cities were treated with either a cardio pump or CPR depending on whether the individual's heart attack occurred on an even number or an odd number day of the month. Before the start of the study, a coin was tossed to determine which treatment, a cardio pump or CPR, was given on the even-numbered days. The other treatment was given on the odd-numbered days. In total, 754 patients were treated with the cardio pump, and 37 survived at least 1 year, while 746 patients were treated with the CPR, and 15 survived at least 1 year. The conditions are satisfied in the study. State the conditions and indicate how they are satisfied. Perform a statistical test to determine whether the survival rate for patients treated with a cardio pump is significantly higher than the survival rate for patients treated with CPR. The conditions needed for a 2-sample z-test are randomness and a large sample size. It is random because the treatments are randomly assigned by even or odd-numbered days. The large sample size is met because the number of patients who did not survive with the cardio pump, 717, and those who did, 37, and the number of patients who did not survive at least 1 year with CPR, 731, and those who did, 15, are all at least 10. We will conduct a 2-sample z-test for proportions with a significance level of alpha equals 0.05. Let PA equal the proportion of patients who will survive at least 1 year if treated by the cardio pump, and let PB equal the proportion of patients who will survive at least 1 year if treated by CPR. The null hypothesis is PA minus PB equals 0, and the alternative hypothesis is PA minus PB is greater than 0. After conducting our 2-sample z-test, we get a p-value equals 0.0011. Because the p-value is less than alpha equals 0.05, we reject the null hypothesis. We have evidence to support that patients treated with the cardio pump have a higher proportion of survival than the ones treated with CPR.